students, today's lesson is on linear functions. So let's go ahead and start with a key idea. And that is that a linear function is a function whose graph is a non-vertical line. So linear meaning that it's a line, and for it to be a function, it cannot be a straight up and down vertical line. Any other type of line would be a function, a linear function. All right, so writing a linear function using a graph. So we're going to write a linear function here. We've done a lot of writing equations for a line. This is going to seem exactly the same since we're writing linear functions. We're going to find the slope. So our slope, we can choose any 2 points. Let's choose these two. 3 minus 0 is 3, and 4 minus 2 is 2. So our slope is 3/2, and our y-intercept is at -3. So our linear function will be y equals 3/2 x minus 3. We can also write a linear function using a table. So again, let's start by finding the slope. Our change in y here, I'm going to show the subtraction this time. We'll do 9 minus 7 and -3 minus -2. So 9 minus 7 is 2. -3 minus -2 is -1. So our slope is -2. Now we need the y-intercept. We see that when x equals 0, y is 3. So our linear function is y equals -2x plus 3. All right, let's look at a real-life example. So here we're controlling an unmanned aerial vehicle for surveillance, and the table shows the height, y, in thousands of feet of the UAV, x minutes after you start its descent from cruising altitude. Okay, so we can see that, of course, the height is decreasing because we're descending, and we need to write a linear function. So we're going to start by finding the slope. Let's do that right here. So our slope, will do 60 minus 65 is -5, and 10 minus 0 is 10. So that means our slope is -1/2. And we need the y-intercept as well. We can see at 0 minutes, we're starting at 65,000 feet. So our linear function will be y equals -1/2 x plus 65. Okay, so graph the linear function. Let's go ahead and label our axes. So we know that x is minutes, and y is height in thousands of feet. Okay, and let's see, we'll go ahead and count by tens here. 10 minutes, 20 minutes, 30 minutes, 40 minutes. That's probably enough. And then I'm going to count by tens here as well. So 10,000 feet, 20,000 feet, 30,000 feet, 40,000 feet, 50,000, 60,000, and 70,000. Okay, so we know that we start at 65,000 feet. So we're right up here to start with. And then every minute, we're decreasing by half a thousand feet, so 500 feet every minute. So that means that after 10 minutes, we're decreasing by 5,000 feet. So we'd be at 60,000 feet after 10 minutes. We'd be at 55,000 feet after 20 minutes. We'd be at 50,000 feet after 30 minutes, and so on. Okay. So this is going to be our line. And find the height of the UAV when you stop the descent after 1 hour. So in other words, when x equals 60. So we can use this equation of our linear function and say -1/2 times 60 plus 65. That means that y is at -30, so it's decreased 30 feet from its starting altitude 30,000 feet from its starting altitude of 65,000 feet. So y is 35 or 35,000 feet after 1 hour. All right, one more example. So here we're going to compare some linear functions. So the earnings in dollars of a nighttime employee are represented by this linear function, y equals 7.5x plus 30. And then the table shows the earnings of a daytime employee. So first we just have to decide which employee has the higher hourly wage or the larger rate, the pay rate. So here we see the nighttime employee makes $7.50 an hour, and the daytime employee, it looks every hour it's increasing by $12.50. So the daytime employee has an hourly wage of $12.50, which is higher than $7.50. So daytime employee. Okay. Now we're going to write a linear function that relates the daytime employee's earnings to the number of hours worked. So we have a linear function for the nighttime employee. The daytime employee, this is a proportional relationship. So we have y equals 12.5x. So every hour they're making $12.50. There's no bonus or anything on top of that that would give us a y-intercept other than 0 like we have in the nighttime employee. So let's go ahead and graph both linear functions in the same coordinate plane. So we want hours down here as our dependent variable. And let's go ahead and count by ones, but I'm just going to label every other again. Okay, and then our y-axis, our output is going to be our earnings. And let's go ahead and every other mark will count by $10. So 10, 20, 30, 40, 50, 60, 70, 80. Okay, so let's do our nighttime employee first. We know that our nighttime employee starts at $30. So after 0 hours, he's already at $30. And then he'll increase $7.50 every hour. So here we have these divided into tens with 2 sections for each. So we're going to go up like 1.5 squares. So 1.5 squares every hour. Okay, so our nighttime employee looks like this. All right, let's go ahead and do the daytime employee. I'll do that in a different color. So we know that our daytime employee is a proportional relationship. It starts at the origin, and we're going to go up $12.50 every hour. So about 2.5 space or 2.5 squares on here. Okay. Okay. So it looks like this. And it looks like we want to know when those functions intersect, and it looks like it's right about at 6 hours. So after 6 hours, they're going to make the same amount of money. So we can interpret the graph by saying the daytime employee has a higher hourly wage, but the nighttime employee makes money before they even start. So it's not until they work 6 hours that they have broken even with each other, or that the daytime employee will pass up the nighttime employee. All right, that's it. Try a few on your own. I'll see you soon.